previous class, we already have the partial description for quick. And right now, we will continue to talk about the detailed functions of quick, or maybe some of the remaining discussion for quick. So we use UEP instead of TCP. For HTTP version 3. And I don't know, here we have quick to have a function of TLS, part of function of HTTP version 2. And therefore we have a quick, and we can make HTTP version 2 slim here. And for the current HTTP version 2 with a slim version working with quick, then we have HTTP version 3. Well, so this is a current Haskell function to have a new layer, quick. And the quick actually can work with the app layer. For example, HTTP version 3. Well, so quick adopts approaches. Currently, we have the transfer layer, and currently we have some other function, and all the function can be done by app and part of by quick. Well, and actually we mentioned some to have the ARQ. So we have an error, so ARQ. And we have a congestion, something like we have a TCP congestion. And all the layers should be taken by quick, or maybe the app layer. And for connection, for TCP, in fact, we have the connection. For HTTP, we expect to have the connection. For connection establishment, this one should be taken by quick and the app layer. And so that we still have the original function of HTTP. However, for TCP previously, we have the streaming. For example, in chapter 2, we have the concept stream. So we have the streaming for TCP. And currently for quick, actually we should have some individual one. So we have some different way for quick and some other manipulation for quick. And first of all, we gotta know we have TLS. And of course, we still already have the original version TCP. TCP should have the handshake. And then we can have, in fact, we have TCP to have the connection. And we have TLS. Specifically, we emphasize TLS. So, connection for TCP and TLS. And so that we can have the first bit of the data. And currently, we have the TCP plus TLS because we want to use this one compared with quick. But for quick, because it combines the two, therefore, we just have the connection handshaking by quick. Previously, we didn't know about connection. Quick should take the responsibilities. Of course, we have the connection establishment capability by quick. So quick still can have the procedure of handshaking. And after that one, then we can have the first data. Well, if we have the comparison between TCP and quick, then you will know. For the original version, it takes time to have 2 levels of handshaking. But for quick, we just have the handshaking by quick simply. Well, so for this, we want to shorten the time for the connection. Therefore, we have two handshakes for the original TCP if we want to have the HTTP service. However, for quick, we just have one handshake. If we consider TCP plus TLS simultaneously, so of course we have two necessary handshakes. And for quick, because of the combination within quick, so we just have a single handshake. And previously we have the connection. And here we have a quick. So for TCP we have a string, we have a connection. So we have an idea. It's a connection, all the connections should follow the same ID. But for quick, this time, yes, indeed, we follow the principle of streaming and to have the parallelism. And so that we have multiple quick to have the parallelism. Because of parallelism, something like original, if we have a TCP connection, right now, for example, we have 10 quicks. And then for the quick, we can avoid head-of-line blocking. And then we call no head-of-line blocking for quick. Right? So, previously, even we have the idea of streaming for TCP, but TCP we have a connection. And this time for quick, we want to avoid the head-of-line blocking. We can allow parallel quicks to implement the connection, and so that it's easy for UDP and quick to avoid the head-of-line blocking. Well, so the current page just try to eliminate head-of-line blocking by quick, and so that quick allowed to have the multiple connection. Quick 1, 2, 3 to the others, and so that we still have the concept of a string. However, we have the parallelism in the current implementation using quick for HTTP version 3. Alright, so look at this. We have TCP RDT. Because of RDT, so we have a connection there. We have a connection ID there. But for quick, yes, we have a connection, but we have multiple quicks. So the current version, we can eliminate possible head-of-line blocking in the TCP scenario. However, if you care about, okay, if you just focus on the quick connection, yes, should we have the head-of-line blocking? Yes, if you try to focus on that part, maybe you still can find possible chance. However, we'll try to minimize that one. So that head-of-line blocking effect will be disappeared. So we think it should be no head-of-line blocking for quick. And here, I already have the HTTP using TCP, so we have a connection ID. And for quick, actually we have a multiple one. Yes, we have some possible connection for each quick, but this time it won't be necessary to have the connection ID for the TCP label. Alright, so that's all for the evolution. In fact, the evolution that it have one idea. If indeed over past 40 years, TCP even that it have some possible benefit. If you don't like it anymore, then you can do it for yourself. Therefore, what's the possible choice? You can apply. You can apply UDP and implement your own function. For example, HTTP version 3. Well, that is the possible chance for the evolution. And of course, maybe in the future, we still have the other possible version for the transport layer protocol. But at this moment, we already have the possible way using UDP with your own app layer application. Alright, so that's it. We almost finished all the discussion for chapter 3. However, I still already have some supplement. And for this one, I call it the supplement. It is called the delay modeling of TCP slow start, because we have one question in this chapter. It needs to know some concept about the current discussion, slow start. Slow start delay modeling. I think up to now you know slow start. How to implement slow start? To implement slow start, we have one new app. Then we increase window size by 1. Am I right? Still remember that? So what does on that version? Because for that version, we may have a different variants to have the slow start. Later we can let you know that one. And first of all, we just want to let you know the time. So we have the current question. Find the time. If we have an object from the web server after sending a request. So we just want to ask you how to have the time calculation. Well, in the following discussion, actually, we cannot care about too much. So, of course, we can have the different size of a congestion window. So we can have the congestion window. And the congestion window can be adapted according to the different congestion level. But here we mention the other details of connection we ignore. And so that we have the delay calculation. And this kind of delay calculation will count TCP connection establishment time. And we will count transmission delay. And we will care about slow start. Sure. So, necessary delay should be connection delay and transmission delay. And of course, because of the slow start, so we have the different window. And different windows so that we can have the possible time. Well, up to now, we list the notation first, just for reference, and later I may mention some notation for you. If you still can remember, I go through the current definition for notation assumption quickly. S, summarize it's the size, segment size, and O is the object size, summarize it's a file. Alright, so S is the segment size, and O is the object size. For example, it's a file. As for the others, actually we make it perfect. So, no retransmission. Yes, we don't have ARQ consideration. Well, for you, maybe you think, no, I want to consider that one. You can try to find some possible paper to incorporate the ARQ. And so that we have the different time calculation if indeed you want to have that case. And as for window size, here we use W simply. And initially, we assume W is fixed. And later we allow W can change. And so that we have the dynamic size. So we have two cases. Initially, we have a fixed W, and then we have a dynamic W. So we can have the real calculation for the slow start phase. First of all, yes, case 1. We talk about the fixed window. And actually, window can be controlled by congestion. So we directly mention congestion window. Why we directly mention its congestion window? Because slow start is the phase, one of the phase of TCP congestion. So of course, it is the congestion window. And for this case, well, even for the fixed window size, we have the first case. The first case is it is not trivial, but we have a 1. And the best one should be this. RTT plus 1 transmission delay. Segment S over R is transmission delay, right? So let us look at this. Initially, we have 2 RTT. Or maybe, okay, remove it. And this is RTT. And then RTT. So we receive the first few bits after 2 RTT. And after 2 RTT, then we have the time. It's a single transmission delay. All right. So up to now, I have a different color to indicate the fundamental time. Oh, sorry. Here. This is RTT plus S over R. So we have the point. The current 2 points, I request to obtain 1 segment, or maybe multiple segments. But the first segment requires multiple segments. But the first segment comes back. If we have for the time 1 RTT and the first segment comes back, and here we have the current time period RTT plus this one, and we have window size R over window size window size W multiplied. So we have the transmission delay WS over R larger than that one. And then it says, currently I have the current time because of the messy situation, so let me remove it. So, something like this, we change it to this side. Here, we have a transmission delay and we have RTT, so we observe it from the other side. So previously we have that time from the center side, and currently we change it to the server side because yes, we pass on the server side. We have the transmission for that segment, and you return your app, and so that I can start it or not. So previously it's the center side, and right now we have the receiver side. Receiver side, once we receive it, then we can do it further. Because the current time transmission delay or the window size transmission delay can larger than that one, so we can continue to send. So this is the first case, and so that the current case says no gap. And maybe no feeling for you for no gap, because later that case, where does it fail? Yes, we have the gap. Currently, where we have gap? Well, nothing. It seems to be nothing, so the time it should be 2 RTT plus O over R. So this is the current situation. And the next one, yes, this one, it doesn't feel, yes, something different. Here we have the transmission delay, and this is RTT, and once returned, however, we don't have a package anymore or segments anymore, so we have a gap here. So this time, we have a gap. Can you find it? For example, we have a 2, and currently window simply from the first one to the second one, just 2. So only 2 and no more. No more packets anymore. And currently we consider the fixed size. So once we have notification back, but sorry, up to now we don't have the segment to send. Alright, so we can have pipelining. And the send, so no, and then we need to wait to the next one because of the fixed one. So we have the gap, and for the gap, we can have the inclusion of the gap. For individual gap, the gap should be the difference. RTT plus 1 transmission delay minus WS over R. However, how many? So we should have the assumption further. If we have K times of a window, then the gap should be K minus 1. Here we have assumption K. K says we have we open the window for K times. K times then about gap should be in between the window, so minus 1, so that it should be minus 1. K minus 1 serving as the gap. And the difference serving as the idle time. Because of gap, it is idle time. So it is the second one. If we have a fixed window W, about the current, specifically the current case. Take a look for 1 minute for you. And of course, feel free to discuss with your neighbor and think about any questions. So about the gap, and so that we have the idle time including in the end-to-end delay. Any questions? Maybe let me make sure. For the current calculation, if we have a gap for the second case, if you think okay, then raise your hands. About the current calculation? No. And no. What's the possible problem for you? Anyone can let me know? Well, you don't understand well. K minus 1. Oh, okay. First of all, we have the problem of K minus 1. Let me result to have the simple example about K minus 1. K minus 1 says, oh, alright, if currently we have window 1 and window 2, so K equal to 2. So how many gaps? K minus 1 gap. And likewise, you can have 3. So how many gaps? 2. Alright, so this is the further illustration about K minus 1. So it should be okay, right? K minus 1, this idea. So K stands for how many times of window open. I mean the open to have the windows. K windows. Open doesn't mean open the air, no. It's we have the window. Open for the data transmission. Previously, maybe you think window open, so it should be the gap. No. It stands for we have a window 1, 2. How many windows? And then K stands for how many windows. Open for data transmission. So this is the first illustration. And any other question? Of course, for students online on YouTube, you can pose the question there. Even I cannot see that one, but if I have time, maybe I can respond to you if you want to show some question using YouTube. Sure, feel free to pose some question there. And so, any other possible question to ask me to explain? And fundamentally, the duration for the gap, it should be okay, right? It's easy. And so RTT and transmission delay is easy. And right now, K minus 1 says we have K minus 1 times of idle. Therefore, we accumulate the idle time there. So we have the current calculation. About this, it should be okay, right? And let us get back to this one. Why this one no gap? For example, here we have a window. Something like window, it should be 3. Machine, it should be 3. Or maybe 4 for 3 or 4 for the current case. If we have the current assumption, maybe we assume window equal to 4. Assume. And here we have this one. 1 cent, and then you say, okay, continue. So I can continue. So we can have a 4 and 1, 2, 3, and 4. So sorry, it should be 4. 3, it is okay. We still have the gap. It should be 4. It should be 4. Yeah. So 4 then says I still have the possible segment here, so I can send. And so that let me have the details for you. Initially it's a 4 here, and next one it's a 4 here, and 4 and 4. Right? So even initially for the 4, we assume a lot of segments to be sent. For the first 4, finish the first one, then eliminate the first segment, so we can allow the next one to be sent. And always we have a 4 there. So you can continue, and then no gap for the first window, sure for the remaining window, no gap. And so that no idle time. In fact, we should discuss the second scenario or the second case, then come back to the first case. And therefore, you want to know, okay, this case is trivial. And so that's why we should have the 2 cases. Case 2 here, and case 1 previously. I renamed, so we have a case 2. And this one should be case 2. And we pass on the 2 fundamental cases. But finally, it's really important. Even finally, you forget everything. However, this is the first term. We should compare to something. What's the quantity? The current quantity. RTT plus 1 segment transmission time. So this one and this you should remember. And as for this one, it's easy. It's just time lasting for the transmission of the segments within that window if we have the full window. So the initial one, this one, at least you need to keep in mind. RTT plus 1 segment transmission. As for this one, why? It doesn't matter because later we will alter W to the different size. However, at least you have the maybe just one, simplest one, window size transmission delay. So W multiply S over R. So this is the transmission delay for all the packets, or all the segments there. Well, for the following discussion, maybe for some notation, it is somewhat like abnormal, but I think you understand this. Actually, this one indeed is equal. However, we just have a question mark. Why we have the equality? Later, we will have some further assumption to have the dynamic size, and also we have the further notation for the current case. Now, we are seeing we have the dynamic window size because of a slow start. Slow start at this, it should be initially 1, and then 2, and then 4, and then 8. So we pass on the exponential with the base of 2. Yes, this is a goal. The goal for us, we want to have the derivation. But finally, we will have the derivation. However, I don't have a reminder. To have the final formula, to keep the final formula important, or maybe to notice all the details for the derivation important. Which one important? Of course, notice all the details for these. Because sometimes if you are asked to have some different case to have the further derivation, to apply a formula, sometimes it's difficult. However, if you know some details and even you want to have your own derivation, that's fine. Go and derive for yourself. So, I want to remind you of the details later. If you can have some details, and yes, I'm a guy to apply the formula, sure. You can remember that formula, but you need to know why and how you can apply that formula. Alright, the two approaches, if you can know some details, that's fine. So, we have a notation, Q, K minus 1, so that we have a minimum value, we denote the minimum value by P. And we have the definition for Q. We have the object size, it should be limited one, the finite one. So we have the natural one, K minus 1, to serve us the idle, possible times of idle. However, Q here, he assumes we have a really large file. And so that really large. And then we just have the, maybe later I can show something. At least keep this in mind. Infinite size first. However, K is not. K just, previously I should then have the formal definition. But here, this is a formal definition for K. Number of a window cover the object. So we have possible this example. We should have the mission to distinguish Q and to distinguish K. For the current example, if we have a really large file, so Q is equal to 2. And if we have the window, if a window cover the size just 2, then K equal to 1. And if we have K larger than or equal to 3, so we have K minus 1 equal to 2. So, For the current example, we have the fixed value for Q. It's 2. Because we have a really large or maybe infinite size of the object. So Q is fixed, it's equal to 2. However, K, if we alter the size of the object, then K can be, it's even 1, 2, 3, 4. But 1 and 2, we have 0 idle and 1 idle. Beyond 3, and then we have idle times equal to 2. So that K minus 1 equal to Q exactly. Because we want to have the different situation, so we want to have the new notation P. So that's why P serving as the real idle times. Why? Because, alright, maybe you have different cases of K, but I always have a single P to denote the idle times. And the idle time, how to determine the idle times? You just choose minimum Q and K minus 1, and then that's done. Why we want to choose Q minimum between Q and K minus 1? Because we want to determine cases for K max K minus 1 determine the gaps. Or finally, it is determined by Q. Right? For example, thinking about if we have K equal to 5. Right now, 5 minus 1 is 4. However, for the real situation, we just have at most idle times equal to Q. So get back to the definition. Infinite size of file or maybe object, Q denote the idle time. So Q actually serving as the at most number of idles. However, K, because K cannot reflect all the possible situations. Possibly K really large, but the idle time only Q is 2 here. And K perhaps is small. Sometimes we have K equal to 2. We just have 1 idle. Or maybe K equal to 1, we just have 0 idle. So we should have the minimum to determine the real idle times. So that's why we have a P. Well, according to the current illustration, meaning for P is okay. It should be okay, right? Alright, so finally, if you forget everything, P indeed denote the types of idles. Here we assume we have 15 segments and K equal to 4, Q equal to 2, so of course only 2 idles because at most it should be Q. And if you don't like it, you can assume K equal to 2. Then we just have a single idle time. Right now, let us have the derivation. And first of all, transmission delay plus RTD. Previously, I asked you to keep this in mind, right? So, we pass on the time to have the comparison. How to have the window? Oh, here it's a W equal to this one. If lowercase k denote case window. How about the first window? The first window using the exponential with the base of 2, it should be 2 raised power to k minus 1. And so, in fact, this is W. And previously, we already have the difference. The current time minus the window transmission delay is served as the idle time. And if this one is positive, then indeed we have the idle time there. Maybe sometimes K increase, smaller k increase, so that this is a minus. A minus saying that later one, the window transmission delay larger than, so it's the first case. First case saying no idle time. No idle time, then okay, no idle. So we can have a plus to enforce this one always positive, or at least it's 0. So the current notation, for example here, A plus says max value of A and 0. For example, A is minus, so maximum value should be 0. Or otherwise, A is positive, so A is 0. And finally, RTT transmission delay, that's fine. We have idle time. Idle time, if exactly we know it's P. Right? Exactly it's P. If we assume exactly it's P. So exactly it's P, so should we have a plus? No, we can eliminate plus. So plus eliminate because, yes, you know idle time is P. So it doesn't matter, this is idle time. Remember this? If we have a P to denote the number of idle time, we don't care about the positive case beyond P. Because beyond P, it should be negative. And negative, actually, we can have k equal to 1 to P, and P plus 1, no P plus 1. And here, it won't be necessary to have a plus. Well, maybe you have a question. Why bothering to have the notation plus? To have a plus is the general description. Maybe I don't know the index, I will go beyond. However, if we have a proper control for P given, yeah, it doesn't matter, we won't have a negative value. So, just have the difference. And once you don't have a plus there, then you can have the final result. You can check it further. Alright, because you just follow the sum of a series. 级数的和，各位还记得吗？ If no, you can use ChatGPT to look up sum of a series. Specifically, it's a geometric series. 几何级数. Alright, so actually, if it's a geometric series, recently I still remember because of my child. This one, if it's A and AR to ARM minus 1, the result should be alright, if you forget this, take a picture, then you have the formula. If finally, okay, you want to look up, you can use ChatGPT or Google to have other result. So it's true, we have this. And after now, I think you know the details for the derivation, and of course, finally you can have the formula as well. Which one you want to use? If we want to apply the formula, do you think it's easy? Not really easy to memorize the formula. So sometimes you can use the step-by-step to derive by yourself. And later we have two possible problems. How to have a K and how to have a Q. K means how many times of the window open for data transmission. By this time, the first size should be 1, and second size should be 2. The third size should be 4. So you see, first size, second size, and the case size. So assume we have a small k, small. And at least all the size, sum of the size should larger than or equal to Q. And if so, through the manipulation, then we have this. And so that we can have this result. because of time, I go through quickly. I think I didn't know the idea. Window size 1, 2, 4, and 2 raised to power to k minus 1. Multiply the segment size s larger than or equal to the object size. So this is the first condition. As for derivation, finally we should reach this one. I think you all know that one. I'll skip it. And because of no time, so I cannot ask you any questions. So let me continue. And how about Q? Q actually based on these clues. When we will have the size k increasing till we have a negative value. We don't want to have that negative value. We should keep it. The largest k will still have a positive value, and then it serves as Q. 我用中文说，这个小 k 最大，一直到它还是正的，那个值就是 Q。 同意吗？因为我没有限制，为什么？走到最后哪一个是变成负的？哎，那就终结了。前面那个数就是最多的 Q。So I don't know a bit in Chinese because it will be easier for you for local students. Sorry, because of EMI, but EMI allow me to have a bit Chinese, so that's why I have the direct way to let you know the meaning of a Q. And you can try, and actually it's a homework, so allow you to do that one. I should let you know if you remember some of application of HTTP, then we have some further derivation. And this one for your reference. But I should start this one because this is a goal for me. And actually for midterm exam to the current discussion. For the remaining, because it's easy. So this Thursday I can let you know further and then it's done. But this one, likewise, I ask you to talk about this, but no time. So serving as a homework. Same. Till 4 p.m. and you can scan. And of course, I will share this hyperlink. Actually, the problem related to our slow start. And let me have a hint for you. A, B, C here actually related to this one. WS over R and RTT plus S over R and larger than or smaller than. And condition A, condition B, condition C. Actually, the three conditions saying the real window size. Larger than something or smaller than something or fall in between something. And so that, sure. How about applying the previous formula once you know? You know the window size fall in between which one. But my suggestion, well, if you know some of the details, you can know the gap. And try to find the gap so that you can fill in the gap to have the total time for the end-to-end delay for the current problem. Alright, so actually it's not easy for me to have the proper time control so that you have enough time to discuss within the class and then get back to finish the problem. However, at least I started and so that I still touch the problem. And the goal for me is okay. So just kidding, I touched down. So I finished all the discussion partially, but this Thursday I will go through the remaining one. The remaining one actually maybe it doesn't matter. So the score for the midterm exam, it is chapter 1 to chapter 3. don't forget to bring your calculator. And similar to our to our quiz, you should answer on the answering sheets. All right, similar to that one. But don't forget to have those calculators so that we won't have a situation you can bring back to finish the calculation. No, for the midterm exam, bring the calculator. But it should be the scientific calculator, not your cell phone. Not your cell phone to have for the calculation. And any other reminders I will let you know through line group. And likewise for the QR for the hyperlink or for the current product, I will send it to the line group and send our deadline, set it to 4 p.m. today. All right, so that's all for the discussion. And finally, this Wednesday we have a quiz number 2. And from the previous content to the current page. And of course, I will have the discussion first, and then that's done. Almost 20 minutes for the quiz number 2. If no, see you this Wednesday. Bye-bye.